Hi, born student. So in this lesson, we are going to discuss the contents in competency level 2.3, which will be uses of Newton's law of motion to analyze any motion of a body. So at the end of this lesson, students are able to understand mainly applies Newton's laws of motion for any system considering state of motion as well as force. So in our previous lesson, we have found that there are a variety of quantities associated with the motion of any object. So these quantities are displacement, velocity, acceleration, and time. So having a knowledge of each of these quantities, so we can have a descriptive information about an object's motion. So please see the slide here. And in this slide, you can see a car. And according to the signboard, 200 meters from here, you have a hospital. So here, the car is moved with a constant velocity of 20 ms minus 1 and towards the west direction, and time taken for the 200 meters distance, displacement of course, is 10 seconds, and which is moving in westward displacement of 200 meters, then we can say the motion of the car is fully described under the situation. Because you know the velocity of the car, which is 20 ms minus 1, which is constant velocity. And here, since it is constant velocity, you know that acceleration is 0. And time is 10 seconds. Displacement is 200 meters. So that is why we can say, considering the motion of this particular car, the motion of the car is fully described. However, this type of completeness is not always known in the case of motions available in universe. So it is often the case that only a few parameters of an object's motion are known, while the rest of are unknown. So in such an instance, the unknown parameters can be determined using mathematical equations, which are known as the kinematics equation. So hope you all can remember, since you have learned these things in your last lesson. So there are 5 kinematics equations, and I hope you can remember these things, such as V equal U plus AT, S equal ut plus half at squared. So there are 5 equations. So we can say that the kinematic equations are a set of equations that can be utilized to find unknown information about an object's motion using some known information about the motion. So using these known information, and we can find these unknown information using the kinematics equation, which you have learned last time. So before I introduce Newton's law, which is the main topic in today's lesson, and I have to introduce you very simple and general idea of force. As you all have learned the concept of force in your ordinary level. And in this slide, which I got from the textbook of grade 9, here the force is simply a push or pull. You can see that one person pushing a car, and then two persons pushing the car, and then three persons pushing the car, and then the car starts to move. So here it's all about push or pull on an object. So if you push on something, or if you pull on it, then you are applying a force to it, we can say. So push and pull. You are pushing something and you are pulling something. So what you are doing is that you are applying a force on the particular object. So we can say that force makes things move. So here that is what happened. So three persons pushing the car and the car starts to move. So we can say that force makes things move. Or more accurately, we can consider that which we have learned in the last time. We can say that force makes change their motion. Because initially, in this example, car is at rest. And then once you apply a force, so car start to move. So we can say that force makes change their motion. And on the other hand, you hope you all agree with me. If I say, considering any motion, and so velocity can be considered as a quantity can use to describe any motion. Because if object is moving, of course, that particular object is having a velocity. So even object is at rest, we can say velocity is 0. So velocity can be considered as a parameter to describe any motion. So now we can say basically force makes change their motion. So we can say that if motion is changed, it means that velocity is changed. So in that case, we can say, if you move a little bit further with this particular idea, and we can say force can apply to change the velocity of any object. So this is what we have learned. Force is simply push or pull, and force can apply to change the motion of any object. Also, we can say force can apply to change the velocity of any object. So please keep these two concepts in your mind, right? So let's learn about force. There are two types of forces available. One is a contact force. So contact forces which act on object when they come into contact with each other, or we can say contact one another. So here you can see a contact between ball and also the player. So you can clearly see it. So there is the contact between player and the ball. And here also we can see a contact. So when we pull the spring, so there's contact. So here also a contact is available. So contact forces acts through a direct contact between objects and object. I mean, they contact with one another. So come into contact with one another. So direct contact is available. And then on the other hand, we have a force so-called long range forces. So which acts on a distance. So forces that can act over distance, so-called long range forces. And here are some examples. So these things you will learn later. This is all about magnetic field, electric field, and gravitational field. And if you have this type of field, let's say if you have a magnetic field and then charged particles are available, So there are forces due to this electric field on the charged particle. So you don't need any contact here. And so gravity basically produces a force that pulls object towards each other, like a person towards the ground. So this is happening due to the gravitational field. So here you don't need any contact. So this is so-called long-range forces. Right. So now we have two concepts. One is force and the other one is motion. Force and motion. So let's think about these things a little bit more. Here, force and motion. So what we have learned, a force can change the motion. Or we can say force can change the state of motion. State of motion. So let's think about some change of state of motion. So in this picture here, you can see a person playing golf here, right? And so initially the ball is at rest, and then once the golf player hit, so ball is moving. So golf ball is moving. So here we can say a force can make a stationary object to move. So this is what happening. So now we have a motion, and it means that there is a velocity because of this case. Here now we have two concepts. One is force and the other one is motion. So we can say that force can change the state of motion. So this is what we have discussed. So force can change the velocity of any object. State of motion. So another word. So let's find what are the state of motions. So here's an example. Person playing golf. So initially the golf ball is at rest. And now golf ball is moving because of the force from golf player. So we can say that force can make stationary objects to move. And then the other picture. So here's an example of, let's say, penalty shoot in a football game. So here that force can stop the movement of any object. So force can use to stop the motion of an object. Now previously force can make stationary object to move, and here force can stop the motion of any object. And also you can understand that force can change the direction of any moving object. So we can take this same example, football. So goalkeeper can change the motion of any direction of the football. So here the force can change the direction of a moving object. Or that you can think force can speed up a moving object. It's something acceleration. So velocity is increased by the time because of that acceleration. And also force can slow down a moving object, deceleration. So we can use force to accelerate object and also decelerate object. So here you can clearly understand force can use to change the state of motion. Stationary object to move and a moving object to stop, and change the direction of any object, direction of moving of object of course, and then speed up the motion and then slow down the motion. However, from the object's viewpoint, there is a tendency of an object to resist. This is so-called natural tendency, of course. Tendency an object to resist the state of change. So natural tendency is available. So we can say that tendency of an object to remain in its existing state. So object, they want to remain in their existing state. They don't want to change their state of motion. So this is a natural tendency. So this phenomenon in physics is so-called inertia. So this is defined as inertia in physics. So here an object tends to stay at rest if it is at rest, or tends to stay moving if it is moving. Because as I said that the objects want to remain in their existing state. So if the existing state is at rest, then objects want to be in rest. If the existing state is moving, then objects tends to stay moving since the existing state is moving. So here you can understand. So there is a tendency to remain in its existing state. So this is natural tendency. This is so-called inertia. So I can say that, let's say object, and keep doing what it's doing. This is what happening. So keep doing what they are doing now, remaining at its existing state. Resistance to change in its state of motion is whole idea about inertia. So keep doing what it is doing now. So let's move a little bit further. And here you have some sort of demonstration and how to demonstrate this particular inertia idea. And you have a coin here, and you just put the coin on a cardboard, and then put the system on a glass. Then when the cardboard is pushed, the coin fall into the glass. This is because the inertia of the coin maintains its state at rest. And the coin fall into the glass due to the gravity. So here you can understand that coin doesn't want to change its existing state. Existing state is at rest. So even you push it, that it just maintain its state of rest, actually, state at rest. And then finally it's fall into the glass due to gravity. So this is what happening here. So keep doing what it is doing. So this is the inertia, the idea of inertia. So this is again this particular idea of inertia. You can see two cars, and one car is at rest. So this car is basically at rest. And so here we can say that car is saying, I'm not going anywhere unless something forces me. And here is a moving car. This is moving. And I will keep doing something, stop me. So here you can understand. So basically, these two cars want to keep their existing state. So keep doing what it is doing now. So at rest or moving. So this is the basic two state of motion. Now here you can understand that in the case of car at rest, so unless something force me, which is at rest, keep doing what it is doing unless something stop me. So you need force here. So you want to start the motion if the car is at rest. If you want to change the state of motion, so you can apply force and you can start the motion of the car. And same time this car is moving, and then you can apply force and you can stop the motion. Here you can see, so you can overcome inertia. So you can overcome inertia. How you are going to overcome the inertia? By applying unbalanced force. So the bottom line is here, state of motion can be changed by applying unbalanced force. So please keep this particular idea in your mind. So you need unbalanced force to change the state of motion, right? If you can apply unbalanced force, you can change the state of motion. So please keep this particular idea in your mind. And also, this question is available: do some objects have more of a tendency to resist changes in motion than the others? I can say, of course, yes. Because the object with more mass having more inertia than the object with smaller mass. So you can have idea. So everyday life, you are experiencing these things. So object with more mass, it's really hard to move. Object with less mass, it's easy to move. So smaller mass, easy to move. More masses, hard to move. So you can understand that. Then the more inertia that an object has, the more mass that it has. So object with more mass is having more inertia. So this is the idea and also connection between inertia and also any motion, object with mass, of course. Right? So in early days of the development of physics, in history, many scientists, including Kepler and Galileo, Newton, so they all developed theories related to motion of object. So the concept of force and motion can be understood through the three Newton's laws of motion. So Sir Isaac Newton can be considered as one of the greatest scientists the world has known. So here you can see in 1686. So here we have 1686. And 1686, Sir Isaac Newton published his three laws of motion in the book, which is named as Mathematical Principles of Natural Philosophy. So here you cannot read this one. This is in Latin. I have just translated this part, and so this is about the book which Sir Isaac Newton has published in 1686. The name of the book is that Mathematical Principle of Natural Philosophy. So his three laws explained how the concept of force and motion work, and how we interconnect this motion and force. So before discuss the Newton's laws of motion, Let's try to understand the concept of frame of reference. So imagine that, so in this case, imagine that you toss up a ball while on a train. So here you are on a train and then toss up a ball. And so let's suppose that this particular train is moving at a constant velocity. So to you, the ball appears to simply travel vertically up and then down. So this is what happened for you. It is up and down. And so this is due to the influence of gravity. However, let's suppose an observer here. There is an observer here. And according to the observer stand there, the ball would appear to travel in a parabola. So according to the observer here, it is appeared like parabola. So here you can understand this particular parabola, this motion with a constant horizontal component of velocity equal to the velocity of train. So now you can understand the different observations occur because these two observers, so one is in train, the other one is observing from outside, are in different frame of reference. So that is why that different observations occur. So then we can define this word frame of reference is that set of coordinates that can be used to determine position and velocity of object in the particular frame. So different frame of reference move relative to one each other. So there are two types of frame of references available. One is inertial frame of reference. The other one is non-inertial frame of reference. So inertial frame of reference, this is really important for us. So inertial frame is at rest or moves with a constant velocity with respect to a given reference frame. So if its velocity relative to given frame is constant, then that frame is said to be an inertial. So then we can simply say the reference frame accelerating relative to inertial frame is not inertial. So in general use, the Earth is considered as inertial frame of reference. Here is an example. Now this is Shinkansen. So this train is so-called Shinkansen. And English name is bullet train in Japan, which is considered as one of the fastest passenger train in the world. Here you can see Mount Fuji. So this is Mount Fuji. So if Shinkansen is moving at the constant velocity, we can say Shinkansen is an inertial frame of reference. So if it is moving with constant velocity, then we can say Shinkansen is an inertial frame of reference. So if it is accelerating, we cannot say. So it's not inertial frame of reference. Hope this is clear for you all. So this is actual picture when Shinkansen is moving near to Mount Fuji. So before move to the Newton's law, so then it's all about inertial frame of reference. And so then we can move to Newton's first law. So Newton's first law stated that an object at rest remains at rest, and an object in motion remains in motion. So in this motion with the constant velocity. So object at rest remains at rest. So this is obvious. If the object is rest, of course remains at rest, unless acted upon an unbalanced force. So this is basically clear. And the second part is object in motion remains in motion unless acted upon an unbalanced force. So this is a little bit hard to understand, because in general that we cannot see that object is having motion with a constant velocity at every time, because there are several forces acting and make resistance for the motion, and then we cannot find this kind of motions. But if you just considering some vacuum chambers and in ultra high vacuum conditions like -6, -7, -8 Pascal, and there are particles moving with constant velocity, and also there are, it's keep moving the constant velocity, and also there are particles in space which are moving in constant velocity and keep moving in the constant velocity. So here the idea is clear. An object is at rest, remain at rest unless act upon unbalanced force, it is clear. And then object in motion remains in motion unless act upon an unbalanced force. So the implication, we can say no changes in its state of motion. No changes in its state of motion unless upon by an unbalanced force, unless acted upon by unbalanced force. So then can you remember that what we have learned considering these two examples of car? Hope you can remember this situation and here. And so tendency of an object to resist changes in its state of motion, which is inertia. And here that if you want to overcome inertia, what you need to apply unbalanced force. So if you apply unbalanced force, you can change the overcome inertia. So here also that if unbalanced force is not there, let's say unless, let's say that if the unbalanced force is not there, then object is at rest and keep in a state of rest. And when the object is in a motion, if there is no unbalanced force, an object is in a motion. So these two ideas are similar, isn't it? So tendency of object to resist change its motion and keep in the motion, keep doing what they are doing. So we can say that keep doing what it's doing with balanced force. So unless acted upon an unbalanced force, we can say keep doing what it's doing. So it's the idea of inertia. So because of that, we can say Newton's first law, sometimes referred as a law of inertia, because that inertia idea is there. So that is why Newton's first law referred as a law of inertia. So before moving to the second law, and let me clarify a few things. And so you know that so if its velocity relative to given frame is constant, then that frame is said to be inertial. So this is what we have learned. So relative to given frame, the velocity is constant. Shinkansen. If the Shinkansen is moving with a constant velocity, we can say that frame is inertial frame. So Shinkansen is inertial frame in that case. So by definition, Inertial reference frame is a reference frame in which Newton's first law is valid, because moving with a constant velocity. Shinkansen is moving with a constant velocity. So Newton's law is only valid in this particular inertial frame. So we can define inertial reference frame as that reference frame where Newton's first law is valid. So we have another definition for this inertial reference frame. And then I have to define another quantity which is mainly associated with motion, which is so-called momentum. So momentum is a physical quantity which is related to motion of an object, associated with motion. So momentum of an object is the product of its mass and velocity. So product of its mass and velocity. So we can define, we normally denote actually momentum by P, then P equal mv is the equation. So product of its mass and velocity. So momentum is a vector, has both the magnitude and direction. So this is the idea of a momentum. So momentum, which is a physical quantity related to motion of any object, and which is the product of mass and velocity. So let me summarize what we have learned so far. So it's all about two ideas, two concepts. One is inertia and the other one is Newton's first law. So a body at rest tends to stay at rest. A body in motion tends to stay in motion. Keep doing what it's doing. Keep doing what it's doing with balanced force. So here the forces are balanced. Then if the forces are balanced, according to the Newton's first law, objects at rest or objects in motion. So in the case of object in motion, which is object in motion with a constant velocity. So object at rest, then v equals 0, and then no acceleration at all. So stay at rest. We can understand this one. Objects in motion, motion with a constant velocity. So if an object moving in a constant velocity, with constant velocity, we can say acceleration is 0. So you all know this one. So stay in motion with the same speed and direction. It means a constant velocity. So here the idea is that balance force, no acceleration. Balance force, no acceleration. Stay at rest, stay in motion with a constant velocity. So this is just what we have learned so far. So here's a situation where that balance force, no acceleration. So what happened in the case of unbalanced force? So basically the Newton's second law answer this particular question. What happened in the case of unbalanced force? So what will happen to an object if the net force is not 0? So Newton's second law. So Newton's second law explained the behavior of objects with all existing forces are not balanced. Unbalanced force. Forces are unbalanced. And in this case, the unbalanced force is proportional to the acceleration of an object. So we can say acceleration of an object depends on directly upon the net force, unbalanced force acting on an object. And also inversely proportional upon the mass of object. So if the acceleration is A, we can say that A is proportional to unbalanced force, and also A is proportional to, inversely proportional to mass of the object. So this is what happening, right? And then, according to the Newton, this is not what Newton exactly stated. And Newton actually stated his second law of motion in terms of momentum. So it's not the case of this A is proper. Of course, it is true, but he stated his law in terms of momentum. So we can say that the net external force acting on an object equals to the rate of change in momentum of the object. So it means the rate of change in momentum. So let's suppose we have an object of mass m. We have object of mass m, and moving with the velocity of u at time equals 0, and change the velocity to v at time t. So then initial momentum is mu, and then the final momentum is mv. So this is change of momentum. Then mv minus mu is a change of momentum. And rate of change of momentum, then we divide by t. So this component is proportional to unbalanced force. So unbalanced force is proportional to mv minus u divided by t, and then we can put the constant to equal the proportional factors. So then F equal kma. Here we consider the definition for Newton, which is 1 Newton is that force which gives a mass of 1 kilogram on acceleration of 1 ms minus 2. So then here we go with this famous equation F equal ma. So we derive from the idea of momentum. Net external force acting on an object equals the rate of change in momentum of object. So here we have an equation of F equal ma. So F is measured by Newton, mass in kilogram, acceleration in ms minus 2. F equal ma is the equation. So Newton's third law, let's move to Newton's third law. So here let's suppose we have two objects, A and B, and they interact each other. And so they exert a force upon each other. So this is the idea. So it means that we have a object A exerts a force on object B. This is so-called FB on A. So this is object A exerts a force on object B. And then we have a object B exerts a force which is equal in magnitude and opposite direction in object A. Force in object A. So hope you all sitting on a chair and watching this particular video. And when you sit on your chair, so your body exerts a downward force on the chair, and the chair exerts an upward force on your body. So this is what happening. So we can say there are two forces resulting from this interaction. A force on the chair and force on your body. So two forces available. Force on the chair and force on your body. So according to the Newton's third law, these two forces are called action and reaction forces. And these action and reaction forces are subjects of Newton's third law of motion. So every action force, there is an equal and opposite reaction force. So the statement means that every interaction as you sit on your chair, so similar example, there is pair of force acting on the two interacting objects, you and chair. So pair of forces available. So here that the forces on the chair, and the chair exerts an upward force on your body. So downward force on the chair, and the chair exerts an upward force on your body. So here you have a pair of forces acting on two interacting objects. So magnitude, the size of the force on the first object is equal to the size of the force in second object, you and chair. So these forces are equal in size, magnitude, and the direction of these forces on the first object is opposite to the direction of the forces on the second object. So forces, we can say forces always come in pair, and equal and opposite action and reactions forces are available there. So every action force, there is an equal and opposite reaction forces. So here are some examples. So every action force, there is an equal and opposite reaction. So here you have a brick, and then you just applying a force here. So action force on brick, and then reaction force on hand. So we have a reaction force on hand. This is action force. And action force on brick, equal in magnitude and opposite in direction. So it is equal in magnitude, opposite in direction, and when you add these things, it is 0. So net force is 0. So same time that you have a forces here, action force on ground, reaction force on brick. So this is reaction force from ground to brick. Action force on ground, this is from brick. So this is also equal and opposite, and equal in size, and then opposite in directions. So here also similar situation. Here you can see a computer on a table, and you have an action force, and then you have a reaction forces. So you can isolate computer here, and then when you isolate computer, and then you have this reaction force, which is normal force. This is denoted by R. This is reaction force, which is normal force, of course. And then you have a weight of the computer. So you can isolate this body and then draw a special diagram, so-called free body diagram. So this is so-called free body diagram. So the free body diagram is basically sketch of the object of interest. So here we consider computer. So object of interest is computer in this situation. So it is a sketch of the object of interest, computer. So you don't need to draw the computer here. So you can draw this type of circle to represent this particular object. And then you have to draw the forces acting on the particular object. So it's all about a sketch of the object of interest, and then the forces acting on the particular object, right? Object of interest and the forces acting on a particular object, so-called free body diagram. So drawing a free body diagram is an important step in solving of mechanical problems, since it helps to visualize all the forces acting on on a single object, where then we can solve these problems very easily, because we can visualize the situation and we can visualize the forces acting on a single object using this type of free body diagram. Right. Then the other force is so-called the tension force. And so previously we learned about normal force, and then free body diagram, and then we have another situation so-called a tension force. So tension forces along the length of medium, so especially force carried by a flexible medium such as rope, cable or spring. So you have a tension force. So this is act like a pull. So this is acting on the particular object. So then we just draw the free body diagram in this situation, and so this is mass M, and we have a weight towards this direction and also tension force to the this direction, right? So this is a free body diagram in the case of tension force. And another example, this is in the case of tug of war, and we have reactions and action forces and available in this particular rod. So you have to know that how to mark these reaction and action forces, and especially considering some forces available in this type of rope. Right? So considering your idea and what you have learned so far, and we can solve some questions to practice that what you have learned so far. Okay, let's move to the question number 1. So question number 1 is a lamp of weight W hanging from a chain. The question is that what is the tension in the chain? So here you have a tension. You have a tension here, so you can mark the tension. So you can mark the tension here, which is T, and tension T acts upward on the lamp, while the gravitation force, or we can say gravity, pull the mass towards down, right? Then we can write F equal ma here, F equal ma, and in that case this is in equilibrium, so no motion, of course, no acceleration. So we just write F equal ma to this direction, and then T minus W is equal to m into 0, because no acceleration. Then T is equal to W in this case. So you have to find the tension in the chain. So given value is W, so you can easily find this one. So let's move to the question number 2. So question number 2, we have a box of mass M pulled by force F. So we have a box of mass M which is pulled by force M, and so this is happening in a smooth surface. So we can say that frictionless surface. So write down a statement for the acceleration of the box, and then the force F at horizontal direction, and we have acceleration, and we just write F equal ma towards this direction, and then you can find A. So what is the normal force acting here? So here if you draw free body diagram, and so this is a object mass M, and force is available to this direction. So we can say this is a horizontal direction or even x direction, and then we have a vertical direction, y direction, and in this in the case of y direction, so no acceleration, of course no motion. Then we can say that the forces in this direction r minus mg is equal to 0, and then r is equal to mg. So it's very easy. So you have to understand the directions, right? Which direction you are going to apply this F equal ma. So drawing free body diagram is something helpful for you to solve this type of question. So today we have only solved two questions because of time constraint, and hope we can solve more questions in next time and also start new lessons. So hope to see you in next lesson. Thank you very much. Stay safe.